Hello guys, can you guys hear me clearly?
Yes.
Okay, so we're going to start now. So before that, I'm going to introduce myself. My name is Nelson, currently a Triple E Year 3 student specializing in robotics and computer vision. So this workshop will be related to computer vision and machine learning as well. So this is the workshop introduction to convolutional neural network. All right, so before we discuss about the technical terms of convolutional neural networks, let's start with what is convolutional neural network being used for. So convolutional neural network can be used for classifying image, post-estimation, then image captioning, as well as image transformation. So first of all, for image classification, you guys can see on the left, on the top left, there are 4 different types of classification. So classification can be determined whether you can actually determine the location of the cat, for example, in this specific image, or you can also do it with localization. So localization, you can kind of know where the image is, but there's only one object, for example, a cat. Another level is object detection. So object detection, not only that you can classify an image, but you can also classify multiple images in a single image. So what do I mean by that? Well, there are 3 objects here. There are 2 dogs and 1 cat. So with 2 dogs and 1 cat, the convolutional neural network is able to detect where is the dog and what is the location of the dog, and where is the cat and what is the location of the cat as well. And lastly, there is instance segmentation, where it is able to not only detect the location and what object it is, but also like know the specific area of that image. Another things that CNN can do is post estimation, which is to determine your motion or your movement of a certain object or a certain image. Another thing that we can also use for with convolutional neural network is image transformation. Like for example here, this is called style transfer using general adversarial network or GAN. So with GAN and convolutional neural network, you are able to transform, let's say you have an image of an house, then you have a specific style of image, which is, this one is a popular image, I believe. And then you can use it to another image and you can transform the style into the specific house. And lastly, convolutional neural network is able to do image captioning as well. So with that in mind, let's start with the technical terms. So convolutional neural network is heavily depends on the neural network itself. So before we start diving into convolutional stuff, let's start with the neural network and some recap. So I believe that most of you guys that have attended this workshop knows at least some knowledge about neural network and how it works. We're not going to dive deep into the mathematical terms, but we are going to like at least give you some basic knowledge of neural network, because this is like the prerequisite for this workshop. So neural network, as you guys know, consists some amount of layers of neurons, and each layer have certain numbers of neurons. So what neural network does is that every neuron is connected to one of the neuron in the next layer. So if you see here, like there are key neurons in the layer X and there are n neurons in layer Y, then for each neuron in layer X, it will be connected to the one node. So it will be connected actually to every node in layer Y. So in that sense, the connection between the first layer and the next layer here, there's a weight. So what weight does, it's giving what is the strength of the connection between the first neuron and the second neuron in the other layer. And then we also have a bias term. So the bias term is basically just like a constant to determine for the neural network. And we have some phi, which is an activation function. So the reason why we need activation function in neural network is that we want our neural network to be non-linear. So if we just use a normal neural network without any activation function, it will be only a linear function. And to introduce this non-linearity, we introduce the activation function, and this will be later explained clearly. So another thing that we want is that this weight should be able to determine exactly what we want. So let's say for classification problem, we want this weight to perfectly have this input and map it to the output. So this weight should be later be changed every time. So how do we change this weight as the training goes by? So we have this backward propagation. So what backward propagation does is that you want to update the weights and you want to find the change in the weights. Every time you want to like do backward propagation, you have a certain metric, or this metric is called loss function. So what loss function is to determine whether you are currently going to the you always want to minimize your loss, because a loss means that there is some error towards your model and you want to minimize the loss. And to do that, you do backward propagation. And what it does is basically it updates the parameters like weight and bias. So once you do the backward propagation, you update the weights, and then you do for propagation training, backward propagation, update the weights, and so on and so forth. So I hope that I explained neural network in the simple terms. And this is the activation function that I was mentioning to introduce non-linearity towards the system. So non-linearity functions such as sigmoid, ReLU is common for neural networks, as this one will introduce nonlinearity for the ReLU function, and sigmoid is actually mapping the function from 0 to 1, which is good for classification problem in the sense. So before we're going to convolutional neural network, is there any question regarding to the neural network? You guys can type it in the chat or just speak it directly. All right. I assume there's no question. So let's get on to what's the difference between neural network and convolutional neural network. So just now I explained about neural network, and now let's go dive into what is convolutional neural network. So as I mentioned earlier, neural networks, all of the layers are connected to the neuron in the next layer. So that means if you have, for this example, let's say you have K neurons in layer X and N neurons in layer Y, that means the number of connection will be K times N. So everything will be fully connected. So everything will be fully connected. And then, so for neural network, let's say we want to process an image, right? We don't talk about convolutional neural network yet. So how would we process this image? Well, what we do is that we know that the image is 256 times 256 times 3, which is the width, the height, and the number of color space, which is 3. So we basically multiply this number out and we factorize it into a one column factor. So the one column factor will be having the number of rows of 256 times 256 times 3. And then if we want to like do this using neural network, then there will be a lot of connection, because if you guys imagine that this number 256 times 256 times 3 will be quite huge number. So actually from the input to hidden layer, there will be a lot of billion connections. Like there are a lot of connections in that specific layer to layer. So you guys need to think about like the number of computational that the computer needs to compute for this single layer. So that means we need to have another way, because I don't think neural network would be much more sufficient. So the first thing is that the number of weights. As I mentioned earlier, if you have the first layer having K, then the second layer having N, then there will be K times N, or in this sense is ON square connections. So is it the best way to connect this neural network? And the answer is actually no for image. So why is it no? Well, if you guys think about the image, let's say you have a pixel on the top left, right? And you have another pixel on the bottom right. Will this pixel have some relationship? Well, it's kind of unlikely to have any of this relationship. But what if your pixel, let's say, is in the middle and your other pixel is right by one pixel on the right? Well, probably this have some relation in it. So we want to capture this relation. So how can we capture this kind of relationship in the image? Well, we can use convolutional neural networks. So where does the convolutional neural networks come in? Well, first of all, convolutional neural network will have lesser connection as it only captures the pixel beside it. So it will have fewer weights, and also it only have the weights for the one near the pixel. So how can we do this? We do it with convolution. And for those of you that haven't learned about convolution in terms of 2D image, I'll explain it briefly to you guys. And what convolution does is just like neural network, we do weighted sum, and this is what we do again. So convolution is basically a weighted sum meant for a matrix. So it's like a dot product for matrix. So convolutional neural networks, the main difference is that, first of all, instead of using dense connection, we're just going to use the connection, the weights near the pixel. So we're not going to multiply every single pixels with the weights. We're just going to use the neighborhood pixel for the weights. And then the second thing is that we only consider the pixels near the neighborhood pixels rather than all the pixels in the image. So how does convolutional neural network consist of? So first of all, convolutional neural network consists of the convolutional layers. So what is a convolutional layers? A convolutional layers is just layers consisting of a convolutional operation. So the input is an image, then we do a convolution in between, and the output is also like an image. But sometimes the image is not really clear for us. Why is it not really clear? Well, we kind of know that image can have a color space of grayscale, which is 1, a color space of RGB, which is 3. But in this kind of image, the output may have a color space more than 3 or 2 or more. So we cannot really like determine the image directly from the color space, but it is still accounted as an image because of the number of color space. It's a bit difficult for us to visualize it, but it's still considered as an image. So first of all, when we're trying to determine convolutional layers, what we need to consider is there's an input. So for the input, we need to consider how the convolutional works. So convolutional is actually done in this kind of manner. So if you guys can see in the screen, this is how convolutional works. So convolution is basically you multiply this this certain this matrix with this matrix, and then you add up the element wise multiplication. So let's say for this one, 156 times -1, 155 times -1. So you add up the multiplication, and basically that's what convolution does. So if you have a 3 by 3 matrix, then the input will be multiplied every time, and it will shift 1 to the right, and after it shift 1 to the right, it will go to the next row, and then it will do the same kind of thing. So that's basically the basic of convolution. And if you guys see on the screen, there's this term called kernel and bias and all this stuff. I will actually get back to this again, but basically I'm just going to show you that what convolution does is you multiply the element wise of the matrix, and then you add all of it. Okay, so is anyone have some doubts with convolution? Okay, all right, then we can carry on. Okay, so now we'll talk about input. So input of a convolutional neural network usually is an image, and image can always be represented using matrix. As you guys can probably tell, if you guys see an image, it can be represented using R, G, and B, which is red, green, and blue. So any image, usually you can represent it either in grayscale, which is black and white, or in RGB color space, which is red, green, and blue. So with red, green, and blue, you have the same amount of weight and the same amount of height. So width and height for this image will be always the same. It's just that the number of color space is actually 3 for RGB. So an image can have several channels, right? As I mentioned, grayscale is 1, RGB is 3. And there are more color space in computer vision. I think there's HSV color space and some other color space. But for neural networks, usually people will tend to use RGB or grayscale. So that's the main thing about input. So what you need to consider is that input of a convolution neural network is an image, and the parameters is W, H, C, and the input of the image, input matrix, which is the image. And then kernels. So for those of you who haven't learned yet about computer vision, kernel or filter is similar to weights in terms of neural networks. And the parameters, so what the kernel does is when you do convolutional with like an image, it will actually give you a feature like edge or corners. So we'll show you after this like what is kernel and all of this stuff. And there are three things that you need to consider for a kernel. So kernel, like what are the number of kernel? What is the size of each kernel? And what is the filter matrix? So the filter matrix is like just now is 3 times 3. So in this sense, the 3 by 3 times 3 is the kernel size, and inside of this is the kernel matrix. And kernel size, this is quite important for you guys because convolutional neural network depends on the kernel size. So kernel size actually explains like how big is the filter or how big is the kernel. So it's usually represented like image, so F times C. So the C here or channel, usually they have the same amount of number as the channel in terms in the first layer. Sorry, in the input input matrix. Yeah, in the input matrix. So what do I mean by that? So let's say this is the number of, so this, let's say this is the number of channel. So there are 3 channel RGB, and the number of channel for the kernel is also 3. So we usually tend to match the input channel with the kernel channel. All right, so that's the main use of the channel. So this is the statement about that just now. So what is the typical matrix size for kernel? Well, it's usually around 1 times 1 to 11 times 11. And what 1 times 1 does is just to, if you have a lot of channel and you want to combine them into less number of channel in the output size, then you can do 1 times 1 convolution. So this is not yet clear because we haven't gotten to the output layer, but later I believe that it will be much more clear once we have gotten into the kernel and the output. So kernel, for those of you who haven't taken convolution computer vision, is basically a matrix. So for this example, as this is an RGB, this is a grayscale image, the channel number is 1. So that means there's only one matrix channel for the filter, which is 3 times 3 times 1. So F times C is 3 times 3 times 1. So when you do convolutional with this specific kernel, what it does is that it will generate this image. Similarly, there's another kernel called Sobel. So what it does is to get the edge detection. So if you do convolutional with two of these, you will get the edge. So that's what I mean by kernel. And the thing is that if you guys know about the history about computer vision, we actually in the in early 21st century, we designed this type of kernel. So like this kernel, we designed this kernel, we designed this. But for convolutional neural network, as I mentioned earlier, we try to replicate neural network so that the weight is actually the kernel. So that means we let the neural network design the kernel. So that's the meaning of convolutional neural network. We let the network design this kernel or weight. So let's get into more about the parameters that we can tune in terms of convolutional neural networks. We have stride. So stride determines how far to move between filter to filter. I mean, how far does the filter move between the layers? So if you guys see here, from this image, you guys can see that it skips one column and it skips one row. So in this case, the stride is equals to 2. So what do I mean when we usually use the stride equals to 1 in the previous example? Well, in the previous example, what we does is that we always do we don't skip any of the pixel. So we actually evaluate all the pixel one by one without skipping one row or one column. But here, in this example, we do some skipping. So this is one of the parameters that we can tune in neural networks, in convolutional neural networks. And the other thing that we can tune is padding. So what padding does is that we want to counteract the number of strides. So what stride does is that we reduce the output size to be very low. So from 5 times 5 into 2 times 2. So it's quite low. So if we want to counteract this, we use padding. So it's basically like the opposite of stride. So the main idea is that we don't want to do a lot of convolution with stride so that as you guys can see, every time we do convolution, the output size will be much more smaller than the input size because of the properties of convolution. So what we do is that to counter this, we use padding. And there are 3 different types of padding. So the first one is full padding. So full padding means that the output size usually is bigger than the input image. And then the second one is same padding. So same padding is when the output image size is the same as the input image size. So size in this case is width times height. Shape is width times height times the channel. So currently, if I'm saying like size, what I'm trying to say is that the width and height doesn't change for same padding. And for valid padding, the size will be much more smaller than the input. So in this sense, if you're doing 5 times 5, and valid padding means you don't do anything for this kind of example. So you don't add any pad. You can see when you do convolution 5 times 5, it will be a 3 times t. And this every time you do a padding, right, that means there is a certain formula where you have an input image size and then the output image size. And this size will be like, we will show you the formula later on. So this formula will be quite important. So before that, I'll show you another example. So in the first example I've been showing you, it's always have been like one types of filter. So remember that I mentioned about the number of kernel or number of filter. In this example, there's only one filter and each filter have 3 different channels. So what if we have, let's say, 2 filters? So this is the example if we have 2 filter. So as you guys can see, the number of channel in the output volume or the output image is actually 2, which is determined by the number of kernel. So we have the first kernel, WO, and the second kernel W1. So these two will determine the number of channel in the output volume. And then we can see that here, if you guys can see, there's actually a padding. So the padding here is actually we add one row and one column in the left, one row and one column on the right and bottom. So basically, the number of the size will be increased by one in this sense. So what it does is that you always add a zero. Usually we do zero padding. So we put a number of zeros in the top one and the bottom one, left and right. So if the number of padding is zero, we do number of padding is zero. That means we don't add anything. If number of padding is one, we add this column and this row. And I think you guys can see that the number of stride is actually 2 because it skips one of the pixel here. So if you guys can see, it skips one. So if you guys can see, for each filter, the number of stride will be the same. So in this sense, the stride is equal to 2. So that means you skip 1 pixel every time. So is everyone clear with stride, padding, and filters? Okay, so lastly, we'll talk about the output size. So we're going to connect everything that we just learned currently. So we have input image, we have the size of the input size, the input image, we have the kernel. So we have the number of kernel, we have the size of the kernel itself, and we have also the number of channels, and we also have strides and padding. So for general, we have this general formula where if you have the number of we have the number of widths in the first image, in the input image, we have the number of kernel, we have the kernel size, which is usually is always symmetric in the sense that width and height have the same size. Like just now it was 3 times 3, so it will be symmetrical in the sense that the number will always be the same. So there's rarely any convolution with, let's say, 3 times 4 or 4 times 3. So usually the kernel will be the same. And then the padding. The reason why there's 2 here, because as you guys can see, we add 1 in the left and we add 1 in the right. So there's the 2. And we divide it by the stride. So this is mainly the formula used when we are trying to design our CNN. We use this formula to kind of know what is the output size and what is the next layer of filter. So a bit of exercise. So I'll give you guys around 2 minutes. So the exercise is determine the output size of each layer. So I'll explain you a bit about what is the question asking. So the width and the height is 32 and the channel is 3. And then as you guys can see here, the filter size is actually 5 times 5 times 3. So this 3 here actually will see from this 3. So as you guys can see, the C or the channel for the input image and the kernel is the same. So I'll give you guys around through 3 minutes to do this. Okay, maybe around 3 minutes should be enough. All right. So I've launched the poll and you guys can try out this example and let me know if there is any problem with the polling. Good luck, guys. Oh yeah, for the second question, I meant is the green layer, not the red layer. Sorry, I mistyped that one. So I give you a hint on the bottom right where you just put the formula. So if you guys want to use that, you can use it for this example as well. We'll be ending the polling in 1 more minute. K is the number of filters. So in the first image, the number of filters is 6. The second convolutional will be 10. We'll be ending the poll in 30 seconds. All right, let's end the poll. So for the first question, majority says it's 28 times 28 times 3 followed by 28 times 28 times 6. And the second one, everyone says is 24 times 24 times 10. So I'm assuming that for the first one, you guys have misconception regarding the K and C. And for the second one, I think like some of you guys realize that actually the K is the number of filters, which maybe I didn't explain that clearly. So I think I'll explain first about the answer, then we can kind of go back to that part where maybe I didn't explain it quite clearly. So this is the answer. So 28 times 6, and the second one will be 24 times 24 times 10. So for those of you who answered correctly, congratulations. And for those of you who have some problems, don't worry, I'll explain it a bit. So as I mentioned earlier, the C here will follow the number of C in the filters. So if there's 3 here, that means this one will always be 3. So we can also do that in a similar way. We see 6 here, which I bolded in purpose. And we already know the answer for this one is 6. So that's kind of a way to cheat this. But another way is just to see the number of filters. So there are 6 different filters for this case. So that means the number of channel here will be 6. And similarly, the number of filters here will be 10. So the number of channel here will be 10. So this 6 will follow this 6, which is number of channel, as I mentioned earlier. Filters do have the same amount of channels, but the number of filters will only the number of filters here will determine the number of channel in the next layer. And this one, which is the filter size 5 times 5, will only play a role in the width and the height. So if you plug in the formula, which I believe everyone can do that, you will get this one will 24 and this one is 28. So I think from the voting or from the poll, I see that you guys don't have any problem regarding the W and H. It's just that the number of kernel and filter. So with that in mind, I hope that just now with the exercise, I am able to explain it more clearly that the number of filters in this layer will actually play a role the number of channel in the next layer. Similarly for this one, it acts the same way. And the number of channel for the filters is actually equal to the number of channel of the input image. So 3, 3, 6, 6. This 6 will play a role in this 6. And this 10 will play a role in this 10. All right, so that's about the first exercise. So I hope you guys are clear with that. And let me talk about the implementation. So now that we already have like clear way of understanding convolutional layers, so how do we do convolution in terms of coding? And the main idea is that we always want it to be a matrix operation. And to do this in matrix operation, where we just like multiply in terms of matrix, not a dot product kind of matrix, but in the sense matrix kind of multiplication, we need to transform it into another matrix. So there are many things that we can do, and the main function is IM to call. So this IM to call is actually depending on what kind of let's say what kind of AI framework that we are going to use. Like, are we going to use TensorFlow? Are we going to use Keras? Are we going to use PyTorch? These three, I think they have different types of representation. So in the sense that this implementation can be different for different frameworks, and this is just one of it. So what you can do is just change the matrix for each 3 times 3, let's say. You can just change it. 3 times 3, by the way, is the number of the size of the filter. So 3 times 3. You can just put it into a vector, then you add it. You can always combine this into a big matrix. So that's one of the way. And the reason why I want to explain it like that is that every time you have a different number of channels, you can just stack it on top of each other. And this is one of the implementation of IM to call. So the reason why I explain it in this way is that once you kind of get the understanding of neural networks, and you guys can see this, like the IM to call, you guys can kind of feel like filters is actually the weight, and IM to call is actually like the input. So this is like a neurons, let's say. As neurons is like we represent it using matrix, and the filters we also represent it using matrix. And once we multiply, we get an output which is represented using matrix. And we can always multiply with the second layer of filters with this one, and so on and so forth. So that's the main idea of IM to call. We want to change this into like neural network kind of sense. So when we do backward propagation and we update the filters, it's in a way is a similar method like neural networks. So, and let's say we want to update the weight. So this one is to get the change in the weight, and then we want to update the weight and do a forward propagation again. In the sense, we can kind of see that everything is in a similar manner as neural network. So we're not going to dive in into like what is the number of filters or this. This is just to give you a brief understanding of neural network and convolutional neural network can behave in a similar way. Like filters is weight, the input rather than neurons is image, and the implementation is kind of similar. So one of the problem even with convolutional neural network, right, is that every time when we do convolution, you guys can probably see that every time you do convolution, it's getting smaller. So the reason for it is because the behavior or the properties of convolution is always making the image getting smaller and smaller. And we can kind of do it, like we can kind of save it with padding, but padding will have some problem with the edge over. If you use this quite extensively, it will have some problems with the one on the corner. So in the top left, top right, bottom left, bottom right, it may have some problem with that. So how can we still solve this problem without throwing any useful information? So the other method is called pooling layers. So with complementing the convolutional layers with pooling layers, what it does is to give you, in the sense that we don't want to like, we still want to have um, the number of size. We still want to have the same amount of size, but we don't want to have a lot of like, we don't want to downsample it to the point where we lose a lot of information. So the idea is that each time when we do pooling layers, what we does is that we try to string it, but we don't want to string the size. So remember the shape, we try to string it like the number of channel, but in terms of the size, we try not to do that. And to do this, we do it in pooling layers. So what it does is that it tries to find the maximum, or depending on what types of pooling. So there are pooling average, minimum, mean, maximum, and mean. And the usual one is max pooling. So what it does is that if you have a certain region, you take the maximum of it. So the idea is that if you use stride, right, you will skip some amount of pixel when you're doing stride, which is not a good way in terms of like if you want to downsample the image. So another method to downsample the image is to use pooling layers. So that's the main idea of pooling layers. So the idea is that, let's say you have this image, which is 8 times 8, I believe. So if you do max pooling, what it does is that you find the maximum out of this 4 pixel, which is actually 6. So you put 6 here, and then you do that for every amount of rectangular. So in this case, the stride is 2 times 2 with the striding of 2. So if if we do this for um, every single image, every single pixels in the image, we'll get this. So if you guys can see, 6, 3, -8, -7, the maximum one is 6, -1, 3, 0, 7, maximum is 7, and we do that for all, and we get a smaller image. So I think just now I explained something wrongly about the downsample, if I'm not mistaken. I'm not sure, but I think I can explain that again. So sorry about that. Just now maybe there was some confusion. So what it does for pooling layer is actually downsampling the image. So because the image is kind of huge, and we don't want to have all this information, what we do is downsampling. So we want to retain the information, but we don't want to have a lot of pixels. So how can we do that without actually lose a lot of information? So that's the main idea of pooling layers. So sorry for some confusion just now. Oops. Okay. And the output size will be similar. So in the sense that when you do pooling, it's like convolutional, but without actually doing convolution operation. So for this case, you just put the same formula and it will be the same as the convolutional layers. So sorry about the confusion just now. Any question regarding to convolution layers and pooling layers? Okay, no question. All right, then we can, all right, yes. The difference between pooling, padding. Oh, okay. So pooling, you try to actually not downsample the image. So you try to add some, sorry, padding, right? Padding, you try to add some pixels on the edge in such a way that you can actually try to manipulate the output size by doing padding. So if you do what we usually do is same padding or valid padding. So every time you do padding, right, you add a certain amount of pixels on the top, left, right, and bottom by the number of padding. And what we add in that specific pixels is actually depends, but usually it's called zero padding. So we add zero in that pixels. So we add a column and we add a row, and all of this inside of it will be zero. So for padding, for pooling, what we does is like convolution, but instead of doing multiplication with a filter, we just find the maximum out of that specific matrix. So let's say the pooling is 2 times 2, the stride is 2. That means out of this 2 times 2, what is the maximum? So 6 is the maximum. That means we put 6 here. And then we do that for every single amount of matrix. So 6, then we have a stride of 2. So we don't do the rectangular here. We skip it directly here. So negative 1307, we get 7. So we put 7 and then so on and so forth. So does that clear you? Okay. Uh, any other question? So what do we do if we have, good question. So that is a good question. So what we do, right, for S, yeah. So for S, right, what we usually do, we put either 1 or 2, and when we implement this in code, so the question is that what we do if, let's say, we have a stride that is not multiple of the W minus F plus 2P. So it will give you decimal number, and it will be rejected when we use like TensorFlow or any deep learning framework. And so what we do usually, we always kind of know that the image will be either a multiplier of 2 or 1. And 1 will be quite obvious because everything can be divided by 1. So what we do is usually we just play with stride of 1 or 2, and we don't do like 3 or 4 because it's not convention and it's not really like make sense kind of thing. Because if you do stride of 3 or 4, you kind of skip 4 pixels. That means if your matrix, let's say convolutional of 3 times 3, you actually skip for stride of 4, you actually skip one matrix that is not convoluted at all. So we don't want to do that, and usually for striding, we always do 1 or 2. And similarly for padding, we usually do 0 or 1. Thank you for the question. Yeah. How much size do we reduce? How much size do we reduce? Which size are you talking about? You're getting a smaller file, right? So when you do convolution or max pooling, the size will be reduced to W2. So if you put any number here, if your padding can cancel out if your padding can cancel out the number of stride and the number of um, the size of the pool or the size of the filter, then you can actually get the same amount of size as the input. So it depends on your pool size or your filter size, your pooling, and the number of strides. So that's depending. So it can be reduced, it can be increasing, but usually it won't be like, it won't be actually reduced. I think it will be, sorry, it won't be actually increasing, it will be actually reduced, or it will be the same size. So when you put this formula by right, you will get, oh, what kind of pooling is better, max or average? Okay, so this is an interesting question. So if you do max pooling, right, you will kind of like remove the noise. So you only want to get the best feature out of it, which is actually good, because you want to get like what is the best feature out of this matrix. So what pooling does is, if you do max pooling, you get the best feature out of this matrix, which is 6. But sometimes if you do average pooling, then let's say the number is 0.00255, then you will get, the number will be average with the 0, which is actually the noise in this sense. So average pooling is not good when there are a lot of noise in the input, and that's why many people usually use max pooling and left out the average pooling in the last layer of the convolution. But in any case, the most general one will be max pooling, as you guys can see, because it not only it filters out the noise, but it also get the best, like the best feature out of those pixels. For full padding, does it mean the file size increases? Yeah, full padding, the file size increases. So usually for full padding, you add a lot of stuff, like the number of p. When you put into the formula, you get a bigger one. It's just that because you put the amount of p in such a way that the weight will be much higher than the previous weight. It's just basically this one. You just put some numbers into the formula just now, and you get a bigger number. That's called full padding. If you put a p in that formula and in such a way you get the same size, it's called same padding. And lastly, the if you put padding but you get a lower size, it's called valid padding. So basically this tree is just a conventional name. So it's basically if you put padding or not, and you put it into formula and you get a smaller one, then you can kind of classify which padding you use. All right. Okay, I think we can continue. So, all right, we can continue. So fully connected layer. So fully connected layer is actually like the neural network stuff that we have learned. So this is where we already get all the features from convolutional and from pooling layers, and we want to use these features to determine like the problems that we want. So let's say we have classification problem. So we will direct this neural network into classification problem. If we want to do regression problem, we will direct this neural networks or the features that we have into regression problem, or any problems that we want. So what it does that is it will actually eliminate spatial information, because all the stuff that we've been doing is actually done using an image kind of sense, with different number of channels, different number of neurons, and different numbers of filters. All of these are using image, and now we're not going to use image anymore. So we'll be using neural networks. So how do we implement this from the output image, let's say from the convolution layers or from pooling layers? So what we do is that we stretch it out, like what I mentioned earlier. So if we have an image, we stretch it out into a vector. So after we stretch it into a vector, we'll do the neural network as usual. All right. And the activation function for our purposes later, I'm just going to explain a bit. So we'll be using softmax activation function. So you know, if every time you use neural network, you'll try to determine your final problem. So if you try to binary classification, you use sigmoid. If you want to do multi-class classification, you'll use softmax function. So what softmax function does is that once you have the output layer and it has been like the loss is very low and everything, so all the training has been done, you put this inside and you put this to the formula, which is basically you just e to the power of the number divided by e to the power of number, all the number here, then you will get a probabilities, and the total probabilities for this will be 1. So if you have an input image, then you put it inside of the convolution neural network. Once it is being trained, you will hope to get the probability of that image having a great highest probability. So that's the main idea of softmax activation function. So it is an activation function meant for multi-class classification. So all right, so this is a recap. The convolutional neural network consists of 3 different layers. Convolutional layers, which is done by doing convolution operation, and it is used to extract features. And the other one is pooling layers. Pooling layers is similar to convolutional layers in the sense that you try to downsample the image, but if we use stride, we skip some pixels. So we don't want to skip the pixels. We use pooling layers, where we can also still use stride in pooling layers. It's just that it's uncommon to do that. And what we do in pooling layers is that it's uncommon. Actually, it's can be used. Actually, depends on the situation. Anyway, so pooling layers, unlike convolutional layers where you do it with kernel, you just do it with taking the maximum or the average. So, like I mentioned earlier, max pool and average pool is the most common one, and max pool is always used usually in the beginning, and average pool is to get the average out of all. This is when all the noise has been filtered in some earlier layer, so that in the last layer you kind of want to average them and to downsample them before you connect it into connected layers. So that's the main difference between convolutional layers and pooling layers. And lastly, we have connected layers. So connected layers, right, is the one that we mentioned earlier. It's just a bunch of neural networks. So it's heavily dense connected. And remember that it has a lot of weights and everything is actually connected. But at these specific layers, we already have extracted all the features. So by right, the number of connections should be lower than the first time we do it without any convolutional layers. If fully connected layers and does that mean the neural network is not capable of determining special features, for example, location and orientation of a cat? So, for this one, this will be an object detection kind of thing. So it's a bit different than this one. So we'll talk about it in another workshop. Actually, we have a workshop regarding to object detection. But for this case, we try to classify. So classify in this kind of sense is that you have only you have an image consists of one object, and you try to classify what object it is. So for this workshop, we'll only do that, and we won't be like try to find the bounding box of where the image is. So that will be an object detection workshop later on in, I think we will announce it later anyway. So for this case, we are not going to find like what is the bounding box, but we're just going to like, we're just going to get the, what is this image? Is it a cat, a dog, or something else, right? Okay. All right. Then, so now let's get into the coding part, right? So we have talked about 3 of these building blocks of convolutional neural network. So what we'll be doing is that we're going to use CIFAR-10 datasets. This is quite a popular dataset for a beginner for convolutional neural network, because not only that it contains only like 10 amount of different labels, but the dataset is free and it's being supported by a lot of researchers, and many researchers are currently like still doing CNN with CIFAR-10 or CIFAR-100. But for beginner, let's start with CIFAR-10 datasets. So the shape is 32 times 32 times 3. So As you guys can see from this image is RGB color, and the size, the width, and the height is 32 times 32. So that's the image that we'll be dealing with. Now, let's start with exercise 2. So this is acting as a recap, and this will be also the building blocks for the for our coding practice after coding session after this. So the idea is that this is our input image. So you can see this is 32 times 32 times 3, and the output is 10. So the output 10 is the number of labels here, which is 10, and the input 32 times 32 times 3 is actually the input shape 32 times 32 times 3. So that's the main idea that we're going to do now. Can we apply CNN on 1D signal data set? Well, for 1D signal, usually we just do neural network kind of sense or time series analysis. CNN is more applicable towards image because of the convolution properties. But the filter must be, yeah, the filter 1D is similar to just applying a normal neural network in that kind of sense. Because convolution and neural network is kind of similar in terms of multiplying the weights with the input, whereas this one is filters times the input, so it's kind of similar. Anyway, let's start with the second exercise. All right, this should be fast, so maybe around 2 minutes or 1 minute. Yep. So what are the names of the layer in red, green, blue box in order? So what is the name of the layer in this red, this one green, and this one blue? What are the name of the layers in order? I think we can end it around 20 more seconds. All right. Yep. The answer is correct. So the first one, the red one, is convolution layers. And then the second one, the green one, is pooling. So if you guys can see the pattern, is usually convolution, pooling, convolution, pooling, convolution, pooling, and so on and so forth until you guys reach the pattern. And the arrow here actually is actually this kind of thing where this is actually the convolution part and this is the output. But I think you guys can like kind of get the sense of it. So this is like the convolution, this is like the pooling. And lastly, once we already like get a lot of features, like 2 times 2 times 512. So this is the amount of features that we are going to use. We flatten it out and we put it into a neural network. So with the neural network, the last one will use softmax to get everything into 10. After we get that, we do the softmax and we see which image belongs to which class. Yep. And I add additional ReLU. So ReLU is just, as you guys probably know, when you're doing neural networks, you always try to use activation function. You always try to use activation function in the sense that you want to introduce nonlinearity. So this is why we use ReLU. All right. So do you guys need any break time, or we can continue with the coding session? So with the coding session, I was planning to do it like this. So the idea is that with this kind of workshop is a bit difficult for all of us to like do the screen, see at the screen at the same time do some of the coding. So my idea is that you guys can open this link, and then while you guys are opening this link, this is kind of like a break time for me and for you guys to open the link. So I think we can do the break time as you guys are opening this link, and we can start around 5 more minutes into the coding session. So we have a break time around 5 minutes from now. For those of you who haven't used this is using Google Colab. So I'm assuming that all of you guys have a Google account. So open it with Google Colab and do the instruction on the first column. So the first instruction I think is to copy it to your drive and change the runtime to GPU. The link I have posted into the chat so you guys can directly see it. So for those of you guys who are not sure what to do, just open the link that is posted in the chat. So the tinyurl.com. So I'll post it again in the chat. And then, oops, wrong one. Oops. Yeah, this one. The tiny URL. Correct. tinyurl.com. Yeah. After you click that one, you press open with Google Colab. So if you have a Google account, which I assume that all of you guys have a Google Gmail account, when you press that, it will redirect you to an open one. Yeah. And yeah, I think for some of you who haven't used Google Colab for the first time, I think you can follow Yishan in the comment, which is to connect more apps, then press Google Colab. Okay, I think we can start again. So I hope you guys have a wonderful break just now. So we can start coding session. So don't forget to change the runtime type to GPU and press save. And now let's start with the coding session if you guys don't mind. So as I mentioned earlier, the dataset is CFAR10, and CFAR10 dataset is quite popular. So the first thing that we need to do in this Google Drive or in this Google Colab is to download the dataset so that we can manipulate it and we can feed it into our neural networks. So what we need to do is that I have created this specific cells where it will actually download all the Spartan datasets into the drive. So later in this folder, in the files in the left, there will be this specific folder containing the Spartan dataset. So once I run this, we will see that there will be something later on. So once it's downloaded, we will see that there is a CFAR10 datasets. So let me check whether I have it or not. Oops. Content. Yep, I have the CFAR10 batch file. So I believe you guys will have this. And anyway, I'm going to do the coding first, so you guys don't have to like run backward and forward. So later, the parts where you guys need to like do it yourself is on the bottom part. So for now, I'm going to explain, and you guys can just focus on the screen with me. And later on, I'll give you some time to play around with the collab. So for now, you guys will just follow around with me and see what I'm going to do and see what are the interesting parts of this. So after we download all the CFAR10 datasets, we need to prepare some library that can show this image into the Google Colab. All right. So we'll import some of the module. And remember that there are 10 different labels. So I just hard coded this, like I type everything because there are only 10 sets of labels. which is airplane, automobile, and so on and so forth. So I'm just going to run this. So later what it does is that it will convert the name from numbers 0 to 9 into name. So airplane, automobile, bird, and so on and so forth. Because it is from the data set, it is 0 to 9. So this is just for us to display the thing so that we can actually read it. So this is where the important parts come in. So the idea is that the image is actually 32 times 32 times 3. And when we multiply all those numbers, we get 3072. And then you guys can see in the left, there are data batch 1, 2, 3, 4, 5. And each data batch, so let's say data batch 1, will contain an image of 10,000. So there are 10,000 images, and each image have a shape of 32 times 32 times 3, or 3072. So if we're using TensorFlow for this one, and we're going to use that, we need to change the shape into a specific type or specific shape that the TensorFlow wants. So in this situation where we're using TensorFlow, we're going to use NHWC. So N is the number of image, which is 10,000. So we don't need to change that. H is the height, W is the width, and C is the channel. And when we're doing the workshop, we're using WHC, but width and height for image usually is kind of symmetrical. So when we have not symmetrical kind of size of image, we try to make it symmetrical by doing reshape, or we try to stretch it out using OpenCV or stuff. So what we need to do is that we need to change our image from 10,000 times 32, 3072 to a specific format, which will be done here. So this is the implementation of IM2call. So the given batch will give you in terms of 3072, which is, as I mentioned earlier, 32 times 32 times 3. So we need to change this into a specific format, which is NHWC. So how to do that? Well, there are two different steps that we need to take care of. The first thing is that we need to change it into 3 times 1024, where the 3 here is the number of channels corresponding to the channels. So we'll divide this into channel. And then after we divide it into channel, we'll divide it into weight and the height. So when we do using NumPy, we'll get it directly from this one to this one, from the top one, 3072, to 3 times 32 times 32 using the reshape function. However, with the numpy.reshape function, it's not enough because we still have it in terms of N, C, H, and W. So we need to transform this again into N, H, W, and C. To do that, we have a transpose function. As I mentioned earlier, with this 3 times 32 times 32, TensorFlow and Matplotlib is not expecting this kind of format. Rather, it's expecting in this kind of format. So with transpose, we'll do that, and it will basically change it into this format. So in summary, what we do is that we reshape it using numpy.reshape into this kind of format from here. So this is the given from the batch. We reshape it into the one we know, which is 32 times 32 times 3, but it is written as 3 times 32 times 32, and we'll transpose it. So how transpose works is that it sees the location of the first one. So currently, when we do transpose, right, the 3 location is currently index 0, 32 is index 1, and 32 here, the other 32 is index 2. So what transpose does is just to rearrange the location from, for the first index 0 will be located in the third one, as you guys can see. So this is the first one, second one, and third one. So it will be changed into the third one. And then the index 1 will be changed into the first position. And then the index 2 will be changed into the second position. So that's how the transpose works. And here, you guys can see that we do the same thing. So we do reshape and transpose. But here you can see that it's not actually 120 and it's actually 231. And the reason for this is that we have the n. So the n is not accounted um, in this uh, in this illustration. But for our case, we have the n of 10,000. So because the 10,000 or the n is not going to be changed to another position, so we're just going to leave it there and we put it 0. And now you guys can see that if we minus off 1 from this one, so 2 minus 1 is 1, 3 minus 1 is 2, 1 minus 1 is 0. So this will be in the same syntax as this. So because we don't want to move the number of image, we just leave it as 0. And this is the implementation of IM to call in terms of TensorFlow. So is there any question regarding to the preparation of data? Okay, no, so we'll run this. All right, so yep, correct. And now let's explore what are the data. So I've created a function where you guys can actually display what are the statistics of the data, like the number of image and the number of image in a specific class. So this is the function that I've created for you guys, and you guys can play around with this. So let's play around with the image. So let's say I want to choose out of the 5 batch here, I want to choose the batch 4, and in the batch 4 there are 10,000 image. So let's say I want to choose the sample ID of 100. I just put 100 here. Then when I run this, it will give you a specific image in the specific batch. So batch 4, image 100 is actually this. And what is this? This is actually a frog. So the label ID is frog. The shape is 32 by 32. And it will tell you that the minimum value, so in a pixel, the minimum value will be 0. The maximum value will be 255. But in this image, there's no 0. There's only the minimum value of 8 and the maximum value of 211. And let's take another image. Let's say from batch 5, sample maybe 1000. So this is for you to play around with. So from batch 5, out of 10,000 sample, we take the sample ID of 1000. So this is a horse. And now we see that the minimum value is not actually 11, is it? Last time it was 11, I think. Now it's 28, and the maximum is 228. So there's a problem with this. So we can see that for each different image, right, there are different types of like minimum value and maximum value. And we kind of need to normalize this image because the minimum value is different for each image, and the maximum value is also different. So we need to process this. All right, so how are we going to do that? So we need to normalize it. So the normalize for this specific data should be easy. We just need to normalize it to between 0 and 1. And one of the easiest implementation in computer vision is to use min-max normalization. So what it does is that all the value now will be from 0 to 1. And the function is just this function. So for those of you guys who are not quite sure about normalization, normalization is basically to normalize your data from 0 to 1. In the sense that when you're trying to use some algorithm, if you have a value greater than 1, then it may cause some problem. So I will address this problem later on. But some of the example here for normalize other than the min-max normalization is sigmoid. So as I mentioned earlier, sigmoid is an activation function. And you can see that when you apply this function into a specific input, the output will be always bounded from 0 to 1. And this is what we are trying to do. And this is great. But this is not what we are going to implement in this workshop. Another thing is that we have ReLU activation function. So the ReLU can take the input from zero, the input from negative infinity to infinity, but the output will always be 0 to infinity. However, as I mentioned earlier, the ReLU function is basically just to introduce non-linearity, and we don't want to have negative value. So that's the main idea of ReLU activation function. So why do we want to use min-max normalization for this case? Where, well, this is an image, and image is known for value range from 0 to 255. And usually when we do it with image data, we try to use min-max normalization, as it is a simple one, and it is actually like linear kind of sense. So the main reason why we need to do normalization is explained here. So if we do without normalization, when we do backpropagation, it may cause some issue in the sense that when we do this, it can explode to a number near to infinity or somewhere large, which is not what we want when we are using gradient descent or any types of algorithm for optimizing the loss function. So this is how we implement the normalize. As you guys can see, we just take the minimum, we take the maximum, and we apply to the whole image. All right, so the other thing that we can do is that, remember that our image for the classes, there are 10 different classes, and for these 10 different classes, then we want to have it in terms of factors for each different classes. We want it in terms of factor from, so we have a factor which contains the probability and the ground truth. So the ground truth means is that usually it only consists of a value of one element of 1, and the rest will be 0. So the ground truth means that, let's say the specific element of row 3 is 1. So that means that specific image is actually telling you that the class is equivalent to the row 3. In this case, if we scroll a bit to the up, we can see that row 3 is actually bird. So if we have an image with all 0, but the bird is 1, it's telling you that the bird is actually the image, the class of the image. So that's what we are trying to do with one-hot encoding. So once we run this one-hot encoding, this will give you the factor in terms of 1 to from 0 to 10, and it will tell you which of the image class is it by using the one-hot encoding. So it's easier for us to process the data as using the one-hot encoding. So any questions so far? All right, no question, then I think we can continue. So another question is that for when we are trying to do pre-process, when we have the data, we need to have some way to like, we have, I would say it's like a training pipeline in kind of sense, where we need to divide the data into train, test, and validation step. So this is what we're going to do. We see that there are 6 different batches. 5 of it is training batch, and the other one, test batch, is the one that we shouldn't touch until the end. So if we want to use this 5 batch, we can have it in many ways. Like, let's say we can use 4 of these batch as training, 1 as a validation, and this one for testing. Or another way is to get all these 5 as training, but we leave it at 90% for training and 10% for validation. So this is what I'm going to implement. So for 10,000, we're just going to take 9,000 of it for the training for each batch. So in total, we have 45,000 image for training and 5,000 image for the validation. And this is the pre-process function that I've created for this specific problem. So once we run this will pre-process everything. All right. So with this, we have pre-processed all the batch into 45,000 and 5,000. So let's see whether we can get the 5,000 from here. So what do I mean by 5,000 image? So let me see. All right. If I create a new code here, all right, never mind if it is stopped on the bottom. So if you want to see what are the number of features we have, you just run this code. So if you see here, we have a lot of stuff. So this is basically the matrix of the image represented in matrix. And this is not quite interesting, so because we cannot interpret it directly, but what we can see is the number of valid labels. So the number of valid labels is 0, 0, 0, blank, 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 0, 0, 0. So you guys can see that this is actually the factor containing 0, and one of it will be 1. So only one of it is 0. And you guys can see that the number of image or the number of labels inside of this validation set will be 5,000. So we have accomplished our goal in dividing 45,000 and 5,000. All right. So now I'm not going to explain all of this, and you guys can read it on your own. But basically, this is just an implementation of TensorFlow. So TensorFlow has two different versions, version 1 and version 2. For this case, I'm going to use version 1 because I'm more familiar to TensorFlow version 1, as well as a lot of stuff is already quite, I think most of the module is like quite compatible with version 1. So I'm going to use that because another thing that version 1 offers is that tf.contrib module. So in version 2, they kind of already like combine everything. So it's a bit difficult to use version 2 because I haven't have enough experience. So I'm going to use TensorFlow 1 for this case. And TensorFlow 1 have a lot of features that TensorFlow 2 also have, but the main difference is that TensorFlow 2 have combined most of this stuff. So you guys can read it on your own for how to use TensorFlow 1 and TensorFlow 2. But I think the main things that I'm going to explain is these two, I think. So this is what we're going to use. We're going to use TensorFlow.neural network or .NN. This is to apply the convolutional function. And we also have layers. So this is where we apply our layers like activation function and all of this. We'll apply it in this too. So let's build the network. All right. So we have this image that we already tried for our exercise 2. So this is what we're going to implement. And I want you guys to implement this in your notebook. So before we implement this, I'm going to show you one example. And before that, we're going to import our TensorFlow. All right, so we chose TensorFlow 1, as I mentioned earlier. So this is what we're going to implement. We have this, and we want to implement it in our code. So how can we implement what we have in mind into our code? And remember, all of this, we already used the formula inside and everything so that you guys don't need to use the formula to kind of match all this input and output thing. So this will be easier for you guys. And the entire model, we have seven, okay, eight of these, 1 to 8 is actually convolution and pooling layers. And lastly, 9 to 13 or 14, 9 to 14 is the neural network parts. So what I'm going to do is that I'm going to give you guys an exercise where you guys will fill in all this blank here. And the 9 to 14, as this is not in the scope of the convolution neural network, I already filled it for you guys to just run it. So I'm going to do one example for you guys where you guys can kind of directly fill everything. So the first one is how can we input the filter, and then so this is where we kind of generate the filter. So the filter is generated by just doing giving some random numbers at the beginning with a mean of 0 with a standard deviation of 0.08. So this is just to generate a random number, but we need to specify the shape, and this shape we need to specify it on our own. So let's do it one by one, and I'll give you one example for conv1 filter and conv1 until the first part, I guess, and then the rest of the part you guys can put it in for the exercise. So what I'm going to do for this so the shape should consist of f times c times k. So remember that c is the number of channel, k is the number of filters. So let's take a look here. We want to apply 3 times t, okay? The channel is 3, right? For the first one, RGB is 3. So we have 3 times 3 times 3. And we have 64 different filters, all right? So we'll write it 3 times 3, 3 times 3, and we have 64. All right, so this is what you guys are going to do. Then you guys can continue on ahead. And remember that the formula for the next C is actually the K, the number of filters of the previous layer. So keep those in mind when you guys are filling this. And for the conv1, what we need is we apply the input and we apply the filter. So if you guys can see here, it says you apply convolutional with an input and a filter. All right. So what is our input? Well, this is the input is X. So we're just going to put X here. X. And the filter is the first layer of one filter. Yep. And remember that I put padding the same. Same padding means the output image will be the same size as the input image. The output layer will be having the same size of the input layer. So that's the main idea of same padding. So for this whole thing, I'm just going to leave it as same because I don't want to like calculate what is the size and everything. I'm just going to let it be the same kind of padding. All right. So the ReLU, we apply it into the same filter, same convolutional output. So conv1. Right. And the max pooling will take the input, which is actually conv1. All right. So we put it conv1 here. Conv1. Right. And then these two, we leave it in blank. So what are we going to put it here? So this is the size of the pooling. So why is only these two is blank while the other two here is 1? So the idea is that this is N HWC, right? So that means the N, we want to always analyze all the image. So we don't want to use any kind of thing. We don't want to like use 2 images at the same time and analyze it both at the same time. So we leave N as 1, and we only want to analyze each channel. So we're leaving the channel to be 1 as well. So that's why we are only messing with the H and W. And similarly, in that sense, you don't want to mess with the number of image, skipping the number of image. So the slide must be 1. And you don't want to skip the number of channel as well. So the channel slide is also 1. So that's why you only have 1 and 1 here, whereas this is where you guys need to put in. So if you guys see here, the pooling size is actually 2. So that means we want to have 2 by 2. So we'll put it here, 2 by 2. All right, 1, 2, 2, 1. All right. So this is after you apply convolutional, you apply ReLU, you apply pooling. Once you apply pooling, you apply normalization. So just put it conv1 pool. Right. And I'm going to help you guys that this one or this part is going to be conv1 underscore pn. So what conv1 underscore pn is actually after you apply batch normalization, which is just to normalize the number from 0 to 1. And after you apply batch normalization, this is the output of the first layer, which becomes the input of the next layer. So I'm going to give you guys maybe 5 minutes to fill all of this. And this is like the cheat sheet for you guys. So I'm going to leave the screen like this, and let our team know if you guys have any problem regarding this. So this will be the final exercise for this workshop. And after this, we'll be training our model. All right. So around maybe 8:55, we'll fill all of this back. All right. I think should be okay. Do you guys have any problem with solving this exercise? So I think we can solve it one by one, or I can just copy and paste to the chat first. Let me try it. Uh, so let me try it. All right. I'm not sure whether it will be enough. No. Yep. Oh well. So let me try. Not sure whether you guys can see it clearly or not. So this is for you guys to copy and paste. And I'm going to explain it as I copy and paste as well. So let me know if there's any problem with the copy and pasting. So I'm just going to copy and paste and add some tab. So to add the tab, I'm just going to shift to block everything here and press tab, right? Because Python, they are quite sensitive with the tabbing. Yeah. So I'm going to explain it now. So I mentioned that the number of channel in the second layer must be equals to the number of filters. So that's why it's just copying around, all around. And then 512 is the last one here. 512 different filters. So I don't think this should be a problem for you guys, because basically you just need to copy paste everything. And then this one, you just need to copy paste everything as well for this one. Then for the second one, this one, you just need to also follow the same pattern. So just put the same pattern. And I don't think I changed the number of size and stride. So the size always 2 times 2, so it should be easy for you guys. And this is quite common. I think max pooling, people will use size of 2 times 2 and the stride will be 2. So this is the implementation. And usually the stride will be symmetrical in the sense that 2 times 2 means 2 and 2 here means that we skip 2 in the we skip 1 in terms of the convolution or the pooling for the horizontal, and for the vertical we also skip 1 of it, or we move by 2. So yeah, so I think this should be simple because it's just a copy paste. All right, then we can run this one. Okay, so this is where, so all the networks have been fully created here. So this is where the trainings come in. So this is where you guys can play with some of this stuff. So usually epoch is the number of iterations. So I think this is quite self-explanatory for those who have tried using neural network before, but I'm going to explain a bit. So we have probability batch size, which is usually around 2 to the power of 7 or 2 to the power of 6. And we also have probability. We have probability for whether we want to use dropout or not. And this is to maintain regularization. So we don't want to be our model to be overfitting. So we have some dropout, which is we determine it as 0.7. And the learning rate, where you guys can kind of play, because the model is quite small, you guys can play with the numbers, and you guys, if you guys increase this quite a bit too much, like 0.1, you may not get the the lowest loss that you guys can actually get. Whereas if you guys can change this to 0.001, I think you can get more accuracy or lower loss, right? Okay, so we create logits. So logits is the final one. So once it's outputting it, it will be a size of 10. So this is called logits, and there's a specific meaning of logits because they need it in terms of logits for the model to identify the output. So why not we just give it the logits for the output, because TensorFlow has special kind of variable name, so we can kind of follow them directly. And then we determine the cost and the what is the cost function or the loss function and the optimizer. So for the cost function, we're just going to use, we're using softmax with cross entropy loss. So I'm not sure whether cross entropy loss has been explained in the neural network workshop, but it's not really important. It's just that this is like how can we get the loss or the cost of the neural network model. And we have some optimizer to get to optimize the minimize the number of loss. So this is the cost and the optimizer. And for the accuracy, we're going to use like the normal accuracy, where we can kind of see what are the number of correct prediction over the total amount of number of image sample. So this is what we're going to use for the accuracy. All right, so we're going to run this. So, all right, learning rate. Oh, I forgot to run this one. Okay, right. So once we run this, this is, wait, oh, sorry. This is just to get all the function ready. This is not yet the training part. Sorry, I was confused about that just now. This is just to define the cost optimizer and how are we going to measure the accuracy. All right. So as I mentioned earlier, the cost, the operation optimizer is to reduce the amount of cost, and the accuracy is to get the accuracy of the model. So this is where the training part come in, where you already have the optimizer, you also have the probability or the regularization, and you have the number of, this is the input and this is the label. So just going to run this. And this is to show the statistic every run. So every time it does an epoch and a batch. So every time it does the training and it sees all the number of image in the specific training batch, it will print out what is the loss and the validation accuracy. So this is where we're going to give the batch the feature labels, and this is basically just the function for our model to process. So this is mainly to give the features and the labels into the batches, and this one is to process the training batch accordingly, because the name inside the file is not yet organized. So this is what we're going to do is we're just going to split it into features and labels. So the features is the image, the labels is the one from 0 to 0, 0, 0, 0, 1 or something like that. So it's basically a factor column of 10, as I mentioned earlier. Now this is where the training comes in. So basically we have 10 epoch. So we're going to run this over 10 times. And we have 5 number of training batch here. We process batch 1, 2, 3, 4, 5, and testing and validation. So we're going to run everything. So this 5 contains 45,000 image, this one 5,000, and testing, I think 10,000 or something like that. All right. So let's train our model. So every time it finishes training the neural network, it will print out what is the current loss, and as well as the number of, it will print out the current epoch, which batch, and the number of loss. Yep. So this one should be quite fast if you're using GPU runtime. So this one by right should be GPU runtime. As you guys can see, it's training quite fast. So it should be around 1 or 2 minutes. So you guys can kind of run this one as well while I'm doing this. So let us know if you have any problem when training this Convnet. So we can see that the accuracy is getting higher and higher as the loss is getting lower and lower. And we can kind of see that the model is converging for this specific data sets to around 70%, 71%. So we should expect our testing to be around that number. So this can still go maybe a bit higher. And remember that the parameters, you guys can still tune it. For me, I think after doing some testing, I think this is the best one for the validation. So if you guys have a better one, you guys can let me know so that we can kind of try it out as well. But essentially after 10 epoch, which is the number of times it sees the specific batch. So after 10 times seeing that specific data sets after updating all the weights and updating all the filters, you can kind of see that the accuracy is around 70%, 74% for the validation set. So I think you guys can do this as well. I'm not sure you guys, if you guys have any problem, you guys can let us know. And we're going to test it on a test batch. So once we already test it on the validation set, we're going to test it on the test batch. So this is some function to actually, so this is like the function for the testing set. And this one is to display all the image. So if you guys can see here, right, in the left side, you have this thing. So this thing is where if you guys like want to continue your training, you guys can use this file. You guys can use this file. You can kind of download it or change it to somewhere else. And later, if you guys want to continue training it, let's say to more than 10 epoch, you guys can start from this specific model as the starting point of the model. So rather than a random weights, you guys can use this specific file. And once we already run this function, so this function is just basically to show the image prediction as well as labeling them. So what we're going to do is to test it on the test set. So by right, we should get what is the accuracy of the test model. We should also can have a specific, like a specific image, random image from the test where we're going to see whether our prediction for that specific image is correct or not. So we're just going to run this. And we can see that the accuracy is 73.5%, which is not that bad for CNN, for a vanilla plain CNN algorithm. So we can see what are the errors from our from our sample. So this is the example. So we have a car. Our model predict it as a cat. All right, it's a bit weird, but this one is horse. Our model predict it as a cat. All right, same as well, same as well, same as well. All right, apparently out of all of this, it's showing all the false stuff. So I'm a bit unlucky with this run. All right, but if you guys run this, by right, you guys should have like 7 out of 10 the correct one, but I get all the unlucky one. But it's kind of fine to me. So let's see of the softmax prediction. So this one is only showing the best one, but this one is showing the top 3 prediction. So for this image is a deer. Our model predict it as cat, sheep, and bird, which is not correct. The airplane is predicted as cat, sheep, and bird as well, which is not correct. This one, sheep, is predicted as cat, but the second one is sheep. This one, bird, is predicted. So I think I get a lot of unlucky in this case because I don't have the correct one in that sense. But you guys can try out and let me know if you guys have the same problem, because by right, if you run this, you should have the correct labels. So maybe I run it again just for you guys to see whether I was unlucky or not, because sometimes either that or maybe there's something wrong with this. Maybe I have some bug in the code. So let me check whether I have that bug. I forgot whether I have fixed the bug or not, because apparently when I was doing this, I should get a correct one, but apparently somehow I don't get the correct thing. So this is quite interesting for me as well. So yeah, let me check whether I have problem. So correct. Yeah, correct. This one wrong. Correct. Yeah, so I guess I was unlucky. So you guys can try it out and let me know if either there's a bug in the code, because I remember that I already like tried this out beforehand and should be running okay, but apparently maybe I'm quite unlucky with this kind of run. So let me know in the comment, or some of you guys that are currently trying this, to let me know if the accuracy is like this or like there's a bug or something. But I remember that I've like tried this out beforehand, and this should be giving you mostly 7 out of 10 or 6 out of 10 or 8 out of 10. So it's kind of luck based kind of sense. So yeah, let me know if there's any problem with this. Yep. So, so there's a question that is not answered yet in the comment, which I'll answer it now. So for conv1 filter, how do we determine C as tree? So remember that the image is RGB color space. So that means RGB is channel 3. So we put the same channel, the same amount of channel for the conv1 filter, which is 3. Value error depth input of 3 is not multiplier of input 64. We directly use RGB channel for the first filter. Yes, the first layer is always from the input image. So it's currently for this input image is 3. The other question is value error. I think there's a question mark in your thing. I'm not sure. Do you still have this error, McPhee? Fixing. Okay. So let me know if you have the same problem with the error, with the classification. Okay, so I guess I'm quite unlucky then. All right. Then I'm quite unlucky. All right, but it's okay if you guys have a great classification correct. Okay. All right. So you guys can, for those of you who have finished, you guys can play out a bit with the number of parameters that you guys can tune. Like for example, I can show you what are the parameters that you guys can tune. So first of all, you guys can always tune the training parameters, which is all these hyperparameters, which is easier to tune than the other parameters. So the other parameters that you guys can tune is obviously the layer. So if you guys want to have more layers, you guys can add more, but keep in mind that when I was doing this, I already compute the formula for each and every layer. So do have that in mind, so that when you are creating another layer, you need to make sure that your input shape and the filter shape should be in the same kind of in the same kind of channel, and yeah, just follow out the formula and everything. So if you guys want to add more layers, you can put it here. And currently for the neural networks, you can also add some more layers in case you guys want to have more layers. Yeah. Mine is 6 out of 10. All right. So I'm quite unlucky out of all you guys. That's okay for me, I guess. Does the softmax function show you the correct one as well? For those who are saying 6 out of 10. The softmax prediction, is it the same way or? Yep. All right. Okay. So I'm quite unlucky then. Right. Right. But it's okay. Anyway, for those of you who still have problems, do let me know. And yep. And Andrew just now sent a link in the chat. So this is where you guys can put. Is there a relationship between the number of layers and fitting the data to the training set? So the number of layers and fitting the data to the training set, the number of data is not really important. The number of layers determine how much features you want to extract. So like I did like 4 layers of convolutional and pooling in here. So that means if I apply 4 times convolution and 4 times pooling, so I extract kind of like edge of filters in the first one, then edge of filters of the first convolutional output to the second one, and so on and so forth. So you guys can still extract more if you guys want with more number of layers. And actually in like many architectures of CNN, there are more than 4 layers. Actually, there are a lot of layers, but in this practice, we are just going to show you like the simple one because we don't have much time for training. So that's the thing. Is there a relationship? Yep. Does that answer the question, Joe, for the relation? Okay, sure. So so I think we can tell you guys about what are the next workshop related to computer vision that we are going to have. So we have 2 different workshops in this end of the month. We have RCNN workshop as well as YOLO workshop. So for the RCNN workshop, it will be done on 27th of October. And I haven't updated the link yet for this one. But yeah, later I will send you through the email after this for this specific workshop. So I'm just going to give you a brief explanation of RCNN and YOLO. So RCNN is region convolutional neural network. So this is meant for object detection. As one of you asked, what is the special information of the object detection, which is this specific box here. And we will do that in the RCNN workshop. And this is how the RCNN is being done. So basically, you need to extract a region proposal. Once you extract it, then you apply RCNN. And the other one is YOLO. So YOLO is you only look once object detection algorithm. So RCNN and YOLO are quite popular nowadays. And this is quite popular for high accuracy, like 99% accuracy. But the downside is quite inefficient because you need to extract multiple region. And the other one is YOLO, where you already kind of have the number of grid determined at the first time. And you kind of want to get the output bounding box at the end. So there are two different types of algorithm that we are going to explain on this month workshop in computer vision. So I'll be the instructor for the YOLO workshop, and there's my friend that will be instructor for the RCNN workshop. So if you guys are free and you guys want to explore more using the CNN, do come for these two workshops that we are going to facilitate around 27 October and 30 October. The link for the RCNN workshop, I haven't updated yet, but I will send it through the email for this one and this one as well. So you guys can already sign up actually for the new workshop if you guys click the link. Yep. Yep. You guys can sign it already. And this one, I haven't updated the link, but it should be there as well. All right. All right. So that is the end of the workshop. For those of you who have some errors, you guys can stay behind a bit. And before we end the workshop, I want you guys to fill up the link for the feedback. So it's already in the chat, the intro to CNN feedback. And before we end the meeting, we can show our faces so we can post it on our LinkedIn or on our Instagram page. So if you don't mind, you guys can share. You guys can share your video, and we can take a picture together. All right. All right. Come on, guys, don't be shy. I've seen only 10 people currently. Right, I've seen some of you are showing your pictures. Can start taking the picture on 9:30, so you guys can chill down a bit. And I hope you guys enjoyed the workshop just now. Cannot open camera. Yeah, it's okay if you guys cannot open the camera. More minutes, we'll take a picture. Yeah, I'm giving you guys some time. If you guys like have any question, you can ask me now, or like you guys have any doubts or anything you guys want to ask me directly, you guys can put it in the chat. Right, 3 more minutes. I got the signature about a 2 more minutes and we'll take the picture. One more minutes, guys. Come and show your picture so we can have a great screenshot. The RCNM link, yeah, as I mentioned, I will update that in the email, so you guys don't need to worry about that. I haven't updated that one, so apology from me. Yep. Is there anywhere we can obtain easy datasets to use CNN on as practice? Yep, there are a lot of datasets. CFAR 10, CFAR 100, a lot of datasets you can find it in the internet actually. And there are some, I think, some examples of the code as well. So if you guys want to know all of this, you guys can email me or chat me directly after this. Yep. All right, I think we can take a picture. All right, 3, 2. Oh wait, there's another chat. The form was sent. Okay, okay. All right, we can take a picture now. 3, 2, 1. Cheese. All right. Okay, I've taken a picture. So don't forget to fill out the form so that I can improve for the next workshop. And thank you guys. Thank you guys so much for coming for this workshop. If you guys have any query, you guys can let me know through emails, and enjoy using your CNN to your project. Have fun, guys. Bye. For those of you who still have problems, don't worry. I'll be here and waiting for you guys anyway. All right. All right. Okay. Thank you.